We simulated our CTAT earlier. Now let us simulate our PTAT. So to get the PTAT, we said we need two arrangement. One is the voltage across a diode and voltage across diodes connected in parallel. Then we subtracted those two voltages to get the PTAT voltage. So in the slides you can see and the voltage across the diode we got it's as a CTAT, and that is equal to VD equal to VT into ln I0 by IS. Then we connected a array of diodes and we passed equal current through that. So let us do that first. So when we are doing the theory, we said the number of diodes we connected was n. We connected n number of diodes in parallel. So in the simulation I am using n is equal to 2. That is, we are connecting 2 diodes in parallel. So I copied that and I'm copying this diode. Press F3. Now we have two diodes connected in parallel and we are passing through that diode the same current. We are passing through the diode and we named this node as VD1. So here also I am using the same name as VD1 here, and for a single diode we named it as VD. So VD and VD1 are CTAT in nature. That VD we already simulated, and let us simulate that VD and VD1 will be CTAT in nature. Launch ADEL. We need DC temperature sweep. We need from -40 to 125. I am sweeping the temperature, and output I need to be plotted is the VD and VD1. Through both this arrangement I am pumping 5 microampere of current. So same current is flowing through both the circuits, and now I am plotting. I selected to plot VD and VD1. So as we expected, both VD and VD1 are CTAT in nature, and we said to get the PTAT we should subtract VD, we should subtract VD1 from VD. That is the difference between VD and VD1 is a PTAT. So now let's find that. For that I am making an expression. So this is one curve VD1. So we want to find VD minus VD1 minus. So now we made an expression for VD minus VD1, and I am copying that expression here in the ADE. You can select new expression and you can paste the expression here. So I am naming it as PTAT underscore 1. So in the name PTAT underscore 1, VD minus VD1 will be plotted. So I added that to the output. So this appeared here, PTAT underscore 1. Now if you plot, see, your PTAT came here. So these two voltages are the voltage across the diodes individually, and this voltage, the graph in your left side, uh, is the difference between VD and VD1, and we said that difference is equal to VT ln n, where n is the number of diodes in parallel. So you can see in the slides we already derived this expression, that is VD minus VD1 equal to VT ln n, and we said it is a PTAT. So from the simulation also we got the same thing, it is a PTAT. When the temperature increases, the voltage is also increasing. So that is the nature of the PTAT. So then to implement the circuit in reality, we connected a resistor here. We removed all these we removed these current sources and we put a resistor. So this was the second arrangement that we tried, and we said if this voltage, this node voltage, I am calling it as V2. We did the same thing in our derivation also, in our theoretical derivation also we named it as V2. So I am labeling it as V2. And we said if V2 is equal to VD, somehow if we make V2 is equal to VD, then the voltage across the resistor will be a PTAT. That is what we did after deriving the PTAT voltage. And the current through the resistor I0, we derived it as I0 equal to VD minus VD1, that is equal to VT into ln n. So what value of resistor we put? How we will find the value of the resistance? So initially we passed a 5 microampere of current. So to get 5 microampere of current, the resistance value we can find as I0 equal to VT into ln n divided by R. So R equal to VT into ln n divided by I0, where I0 is the current that we require, that we want to pass through the diodes. So I am using I0 as near to 5 microampere. To get that, VT is 26 millivolt into ln n is ln of 2 divided by 5 microampere I need. So that gives me 3.6 kilo ohm resistor. So if we put 3.6 kilo ohm resistor, our current will be approximately equal to 5 microampere. So I am putting that value. .6 kilo ohm resistor I need. I placed it, and now we have to make sure that VD equal to V2. To make sure VD equal to V2, we said in the discussion we have several options for that. One option is to use the current mirror, and the other option is to use op-amp based circuits. We didn't discuss the op-amp based circuit. We discussed the current mirror based circuit. So now I am implementing the current mirror. For that we need NMOS and PMOS. So I select the NMOS and I am putting a large W and a large L, because in analog circuit, to reduce the effect of process variation and temperature variation, we generally use large device sizes. Even though the W by L is 20 by 5, that means W by L is 4, we don't use 4 micro by 1 micro. We use a large W and large L to have less process variation and to have good matching. So I am using 20 micro by 5 micro. One NMOS I placed there. And I need same size NMOS here. Their gates are connected together. Body is grounded. And now I need PMOS also to complete the current mirror. So the NMOS part is over. To complete the current mirror, I need PMOS also. I am using the same dimension. You can have different dimension also. Actually, the dimension of the current mirror MOSFET is not directly related to the current. Current is determined by the resistor that we already designed. So this current mirror is just to ensure that the equal current is flowing through the branches. So the current mirror size has nothing to do with the current. Current is determined by the resistor. Here it is connected. This is the standard simple current mirror structure. So the body of the PMOS is connected to supply VDD, and this VDD I want to connect over here. So now our current mirror structure is over, and we want to check whether VD is equal to V2. So our first simulation is to check whether VD is equal to V2. So I am deselecting the PTAT 1, and I want to plot. Now I don't want to plot VD1. I want to plot VD and V2. So output to be plotted, select on schematic, is V2. So we said with this current mirror arrangement, by the property of the current mirror, then VD will be equal to V2. So let's run the simulation. So these two curves are very close. They are almost equal. You can see this is VD. One is VD and the other one is V2. One is red and the other one is green. So our current mirror is working fine, and VD and V2 are very close. That means this voltage and this voltage are very close. So if you want more, if you want VD exactly equal to V2, you have to improve your current mirror. You can have cascade current mirror and those other more complicated improved current mirror structure for that. And let us plot the currents also. We said in the current mirror structure, the current through the both branches will be equal. So I want to plot the output of the current through the two branches. Let's plot here and here, and run the simulation. So you can see the current is also almost equal. If you want exact equal current, you should improve your current mirror. As I explained earlier, you can use cascode or other advanced current mirror to get exact currents. With this simple current mirror itself, we got almost equal currents in the both branches. So equal currents are flowing through each branch, and Vd is equal to V2. In this condition, we set the voltage across the diode, the voltage across the resistor is equal to Vt into ln N is the voltage across the diode. So here our N equal to 2, that is the two diodes are connected in parallel. So now we want to plot the voltage across the resistor, and we set the voltage across the resistor is a PTAT. So voltage across the resistor is V2 minus Vd1. So we want to plot V2 minus Vd1. So for that I want to plot Vd and V2. I am deselecting those things. Or I can modify this expression. We already have one expression for PTAT1. So let's modify that expression. That is Vd minus Vd1. So now I want V2 minus Vd1. So I am deselecting Vd1 and V2 and run the simulation again. So now the plot is PTAT. We can see as the temperature increases, the voltage also increases. So essentially it is a PTAT, and what we plot is V2 minus Vd1, that is the voltage across the resistor. So now we got our basic PTAT voltage, and then what we did, then we wanted to separate this voltage to a separate resistor. For that I want the equal current to flow in the third branch. For that I am using the property of the current mirror, that is I am copying the PMOS, and I will connect exact same VGS to the PMOS, so that equal current will flow through all the three top PMOSes. That means equal current in all the three branches. So supply is connected. We need equal gate voltages. So I want to connect this gate to this gate. So we already have this voltage here. Now all the PMOS gates are connected. All the PMOS gates will have equal voltage. In our discussion we called this resistor as R1. So here I am calling it as R1, and we have another resistor and copying the same resistor R2. So we said the current flowing through each branch is PTAT, and when we pass that PTAT current through a resistor, it will become a PTAT voltage. So we copied the current through to the third branch, and we passed that current through a resistor R2. R2 value we can change according to our wish. So now I am using the same value as R1 just to illustrate the PTAT structure, and the voltage across this is our final PTAT. So I'm labeling the node as PTAT. Save. Now I just want to plot the PTAT only. So I am deselecting this output to be plotted. Select on schematic. I just want this PTAT. So run the simulation. So now you got a PTAT voltage across this resistor, across R2. So I repeat, initially we started with the difference between VD and VD1. Then we implemented a circuit so that we get VD minus VD1 across this resistor, and we plotted the voltage across this resistor, that is V2 minus VD1, provided that V2 is equal to VD. And then we copied the current through this branch to another branch, and we passed it to the another resistor, and we said this voltage is a PTAT, and we simulated the same thing. Now let us compare the voltage across this resistor and the voltage across this resistor. That is, voltage across R1 is a PTAT, voltage across R2 is also a PTAT. So let's plot PTAT1, that is voltage across the resistor R1, and PTAT, that is voltage across resistor R2. Now you can see they are almost equal. There is a small difference between them, because I repeat that because we used a simple current mirror, so the current through them is not exactly equal. There is a small difference in the current through the branches. If we use some advanced current mirror like cascade current mirror, then we will get exact the same current through all the branches. So if you want to increase the PTAT voltage or something, then you can adjust this resistor R2 to some higher value, like I am using 10 kilo ohms. So if you use higher voltages, higher resistance values, you can have higher PTAT value. Then we can compare these two. See here, this is the PTAT one, that is the voltage across R1, that is this voltage across this resistor, that start from 15 millivolt up to 25 millivolt. But here since we increase the R2 value to 100 kilo ohm, the value is starting from 40 millivolt to 70 millivolt. So by adjusting the ratio R2 and R1 and the number of diodes in parallel, we can adjust the PTAT value, and the PTAT curve we can adjust. So in the simulation I used n equal to 2, that is 2 diodes in parallel. You can have 3 or 4 or whatever the number you need, you can have them in parallel. So according to that, the PTAT value and the slope of the PTAT will change. The PTAT curve will change, and we can adjust the PTAT to our CTAT to cancel them completely by adjusting R2, R1 and the number of diodes in parallel. So the PTAT simulation is over. We will discuss all this once again when we start the BGR design.